Hi, my name is Erica Sawczynec, and I am a senior undergraduate student in physics and astronomy at the University of Hawaii at Manoa. This is a visually guided narration of my iPoster, an Asteroseismic Age for a solar-type star in a wide binary with an M-dwarf. First, let's talk about M-dwarfs. M-dwarfs are the coolest and reddest stars on the main sequence. They are also the most numerous and oldest lived stars in the universe. Lastly, M-dwarfs are low mass and low luminosity, making them some of the smallest and dimmest stars in the universe. But why are M-dwarfs interesting? M-dwarfs are some of the easiest stars to find planets around, which makes them common targets for satellite missions such as Kepler, K2, and TESS. Planets are easier to find around M-dwarfs for a few reasons. The habitable zones around M-dwarfs are closer to the star, which results in more frequent planetary transits. The ratio of planet to star size is smaller, which implies the planet will block more of the star's light when transiting, making deeper transits that are easier to detect. Lastly, the star is less massive, so the planets around the star pull stronger on the star, making the Doppler wobble larger. Two of the big trigger words for this project are astroseismology and gyrochronology. Astroseismology is the study of the oscillations in stars using the visible pulsations to estimate stellar properties such as age. Specifically, we use the term solar-like to describe stars that oscillate similarly to our own sun. Gyrochronology is the relationship between a star's age and rotation period. Stars rotate at different speeds throughout their lifetime, rotating slower over time. Gyrochronology models are usually empirically calibrated. But why do we care about how old an M-dwarf is? Habitability of the planets surrounding an M-dwarf are directly related to the age of the M-dwarf. Young M-dwarfs put off high-energy flares that can damage the atmospheres of the surrounding planets, reducing the likelihood of finding biological life. However, estimating the age of an M-dwarf is not easy. For the regime where we know the ages of M-dwarfs, there is no reliable trend in their rotation periods. Anywhere outside of this regime, we have almost no benchmark stars to calibrate an age-rotation relation, so estimating the ages of M-dwarfs is difficult. The goal of this project is to provide an astroseismic age rotation benchmark for an M-dwarf. Our system, HIP 43232, is a wide binary comprised of a solar-like primary and an M-dwarf secondary. The two stars are separated by 34 arcseconds, and the primary has a measured metallicity of negative 0.03 dex, near solar. We can precisely measure the age of the system using astroseismology of the solar-like star. The system was observed in campaigns 5 and 18 of the K2 mission. Campaign 18 short cadence observations were used to detect the solar-like oscillations in HIP 43232A. The two components are individually resolved thanks to the image scale of the Kepler CCD. Using the Python package light curve, we corrected and detrended the light curve from K2's 6-hour motion. Then we transformed the light curve into frequency space using the Lomskargel method. To model the frequencies, we started by fitting the background using diamonds. For this star, we used 3 Harvey-like profiles, a Gaussian envelope, and an estimate of the constant photon noise. In this figure, the frequencies of interest are boxed in magenta, and the final background fit is shown in red. We identified 19 reliable low-degree modes between 1900 and 3000 microhertz. The final diamond's Lorentzian profile fit is shown here in red with the accompanying a shell diagram. We performed detailed modeling of the star using the frequencies and the MESA stellar evolution code to estimate the age of HIP 43232A. We estimated the age to be about 4.5 billion years. HIP 43232B was observed with K2 and ZTF, which resulted in 3 different light curves. After correcting the light curves, we estimated the period by taking the peak of the periodogram. We estimate the rotation period of HIP 43232B to be about 42 days. Using the Asteroseismic Age and a few other stellar parameters, we modeled the expected rotation period using two empirical models from Angus et al. 2019 and Barnes and Kim 2010, and one theoretical model from Spada and Lanzafame 2020. These models estimated a wide range of rotation periods spanning between 34 and 67 days. We also compared the rotation of HIP 43232b to well-calibrated open clusters. In this figure, the three gyrochronology models show the large spread in predicted M-dwarf rotation based on age. The main takeaways of this work can be summarized as follows. By modeling the oscillation frequencies of HIP 43232a, we estimate the age of the system to be about 4.5 billion years. Using the data from K2 and ZTF, we estimate the rotation period of HIP 43232b to be about 42 days. We find the age rotation relationship of HIP 43232b is consistent with models that require some level of delayed spin down due to angular momentum redistribution in the interior, such as Spada and Lanzafame 2020. Finally, we add a middle-aged M-dwarf benchmark to the gyrochronology sample. There are disparities between the different models compared in this work. The two empirically based relations are extrapolated from fits on solar mass stars. Aside from being heavily influenced by the sun, empirical models are calibrated using young open clusters aged less than 1 billion years. We expect the spin down of an M-dwarf to start with a 1 to 2 billion year period of spin down, followed by an unknown period of time where the M-dwarf spin down stops. At some point in the M-dwarf's lifetime, the spin down resumes, but this time is ill-defined. Based on this, our young open cluster sample doesn't include any M-dwarfs undergoing spin down stall. Thus, we expect that empirical models will always overpredict the rotation period of intermediate-aged M-dwarfs. Theoretical models, like Spada and Lanzafame 2020, assume a radiative core and outside envelope of the star are initially rotationally decoupled. At some point, the core and the envelope recouple and the star begins to spin as a solid body again. During the recoupling, the star appears to have a stall in its spin down as the angular momentum loss comes solely from magnetic braking. Spada and Lanzafame 2020 theorize this effect is significant for stars less than 0.5 solar masses several billion years into their lifetime. Thus, based on the age and mass of HIP 43232b, it is possible that this star has already experienced a spin-down stall. If you have any questions or comments, feel free to reach out on Slack, Twitter, or through email. Thank you for your time.